Hello, today we are going to discuss and review writing valid equations and balancing them. First of all, reactions and equations are kind of like cooking, but you just shouldn't eat anything in the chemistry lab. Just because you can mix stuff together doesn't mean it's gonna make a good recipe and something that you would actually want to eat. So just because you could write something on paper in chemistry doesn't make it valid. In order for an equation to be considered valid, it has to satisfy two requirements. First of all, it has to include correct formulas. What I mean by this is, let's say the problem said you were working with magnesium chloride, and you were torn as to whether you should write MgCl or MgCl2. Which one would be correct? Well, let's think through it. Magnesium ion is Mg2 plus and chloride is Cl minus. When I crisscross those, I would get MgCl2, which would be the correct formula. I would not want to write MgCl because that is not correct for magnesium chloride. The other common pitfall that I see beginning chemistry students make as far as correct formulas is, don't forget the Brinkelhoff elements. So if you have pure bromine, you can't just write Br, you have to put Br2. If you have iodine, you have to put I2. Nitrogen is N2, chlorine is Cl2, and you've got hydrogen, oxygen, and fluorine. Now, I do want to remind you that that only applies if they're in their pure elemental state. So if it says bromine only. If on the other hand it says magnesium bromide, then you have to write the formula for magnesium bromide, or sodium bromide. Sodium bromide would just be NaBr, because sodium is a +1, bromine is a -1, so it would just be a 1-to-1 ratio. The next thing is that you must balance your equation, and in order to balance it, why we have to balance it is so that it will follow the law of conservation, so that it doesn't look like you are creating or destroying substances. So when you go to balance, there are some things that you can change and some things that you can't. You can change the coefficients, the large numbers out front, but you absolutely cannot change the subscripts. And the reason why you can't change the subscripts is that that would actually violate rule number 1, which we just discussed, because if you change the subscripts, you are totally changing the compound. Today we are going to begin working on adding phase labels to our balanced equations. Some of you who took chemistry last year already have learned this. Some of you that had chemistry last semester, we didn't really get to this very far, but the phase labels tell you what state the substance is in, which is really important. It's kind of like in cooking. Some recipes might call for solid sticks of butter, while others need you to melt the butter, and there's a big difference in which you're using. So if you need something that's in a gas or a vapor phase, you're going to put a G in parentheses after the substance. If you put a cursive lowercase l, that means something is liquid. If you put an S in parentheses, that means it's solid. Or if the word equation says that it's a precipitate, precipitates are solid. Aqueous is the fourth phase label. It's an AQ. Aqueous is what you use when something is dissolved in water, or if it's called a solution. Acids are always aqueous. The main thing is that water itself is never, ever, ever aqueous. Water itself will always be a pure liquid if it's called water. It might be called water vapor, which means that you would put a gas, or if it's called ice, that's solid water, so you would put a phase label of S. As far as trying to figure out what phase label to put if there's not a verbal clue in the problem, if it's a pure element, you can look it up on the periodic table and the color coding will give you a hint. Remember, most metals are solids, most nonmetals are gases. Bromine and mercury are the two liquid elements. Molecular compounds, now remember, molecular compounds are made entirely of nonmetals. Those are a bit tricky. They are usually either a gas or a liquid, and I'm going to generally give you hints about them, verbal clues in the word problem, and you're just going to become more familiar with this as you go along. Some common examples: carbon monoxide, that's a gas. It is around us. It's a toxic gas, so we don't want a bunch of it around us, but I feel like you ought to know that carbon monoxide and carbon dioxide are gases. Water is a liquid at room temperature. NH3 is a substance called ammonia. It's a common chemical we're going to work with. It's a gas. For ionic compounds, now remember, ionic compounds are when you have a metal plus a nonmetal. If there's no water around, those ionic compounds are always solid. But if there is water or anything that's aqueous around, we have to consult these things called the solubility rules, which on tonight's homework, there are solubility rules listed here for you. You have to read and apply these in order. And if there's two rules that seem to contradict each other, the rule that's higher up on the list will win. And that's the one that you're going to go with. I will always give you these solubility rules on quizzes and tests. So you don't have to memorize them, but we want to work on using them today. So and something I do want to point out, if the solubility rules say that something is soluble, that means it can be dissolved, so it's going to get the phase label of aqueous. If, on the other hand, the phase labels or the solubility rules say insoluble, that's going to be a solid precipitate. So a common mistake I see students make is they'll say soluble, I'm going to put an S. Don't do that. Soluble means it can be dissolved and it's aqueous. So let's take this and apply it to a couple examples. All right, so our word equation says magnesium reacts with hydrochloric acid to form magnesium chloride and hydrogen. I'm going to begin by writing my formulas. Magnesium is capital M, lowercase g. It is not a Brinkelhoff, so that's all I write. You might recall that magnesium is a metal that we've worked with in lab before. It's in the solid state at room temperature. If you weren't sure, you could consult the periodic table in your textbook or in my classroom for the color coding on that. It reacts with, so I'm going to put a plus sign, hydrochloric acid. We reviewed the naming and writing formulas of acids. Hydroblankic acids, remember, come from ide anions, and chloride is H-. So when I add a hydrogen to that to turn it into an acid, the formula becomes HCl. The phase label is going to be aqueous because all acids are aqueous. To form, I'm going to put a yields arrow here. We had discussed earlier that magnesium chloride is MgCl2. Now, that is an ionic compound. So I have to consult my solubility rules because I have something that's aqueous. So that means that water is present. So let's go look at our solubility rules. We're looking for anything that applies to magnesium and or chloride. So rule number 1 says all alkali metals, lithium, sodium, potassium, rubidium, and cesium, and ammonium compounds are soluble. That's not very helpful for us. Doesn't include magnesium or chlorine. Rule 2, all acetate, perchlorate, chlorate, and nitrate compounds are soluble. Again, does not help us. Silver, lead, and mercury 1 compounds are insoluble. It doesn't apply to magnesium or chlorine. Number 4, chlorides, bromides, and iodides are soluble. Bingo, we have a winner because we're working with magnesium chloride. So this says that it's soluble. So if I go back to what I'm working on here, soluble, remember, means aqueous, so I'm going to put AQ. And then magnesium chloride plus hydrogen. So I'm going to put H, but hydrogen is a Brinkelhoff, so I need to put a 2. And I'm going to put a phase label of gas. Now, all of my formulas are correct, but I have to see if this is balanced in order to satisfy the law of conservation. So I'm going to draw my little border line between my reactants and my products to make sure I'm not losing or gaining anything. So I have magnesium, hydrogen, and chlorine as my 3 elements. I'm going to list those. Then I'm going to count them up. All right, magnesium, there's 1 of them. Hydrogen, 1. Chlorine, 1. On the right side, 1 magnesium, 2 hydrogens, 2 chlorines. So I am not balanced. I have 2 hydrogens on the right, 1 on the left, 2 chlorines on the right, 1 on the left. I have to put a coefficient of 2 out here, which gives me 2 hydrogens and 2 chlorines, and this is balanced. Now, as far as classifying my reactions go, your reaction types are combination, decomposition, single replacement, double replacement, or combustion. Let's use a process of elimination here. This absolutely cannot be combustion because it's not reacting with oxygen to make CO2 and water vapor. It cannot be decomposition because I'm not starting with one thing and breaking it down. Likewise, it can't be combination because I'm not starting with two things and forming only one. So is this single replacement or double replacement? Well, a single replacement has to have one lone element reacting with the compound. Double replacement has two compounds reacting. If I look at what I've got here, I have the element magnesium reacting with the compound to make a new compound and an element of hydrogen. So this is a single replacement reaction. Let's go to your homework and do problem number 1 together. I apologize because it got a little cut off on my diagram here. But it says lead will react with hydrochloric acid to produce lead 2 chloride and hydrogen. All right, so lead is Pb. It is not a Brinkelhoff, so I don't write a 2 for its subscript. Lead is a solid when I consult my periodic table. Reacts with hydrochloric acid. We just used that, so we're going to put HCl, aqueous, to produce. Now, lead 2 chloride. So lead 2 is Pb2 plus. Chloride is Cl minus. When I crisscross those, I get PbCl2. Now I've got to go to my solubility rules to decide if this is soluble or not, because I do have water present since the hydrochloric acid is aqueous. Okay, let me erase these things. Whoops. Our notes that we had made the last time through. We are looking for a rule that deals with lead 2 chloride. Okay, we already had found the rule the last time that said that chlorides are soluble. But if you look, rule number 3 also says that lead is insoluble. So we've got conflicting rules because rule 3 says it should be a solid, but rule 4 says it should be an aqueous solution. What I said, remember, is that the rule on top wins. So in this case, rule 3 will trump rule 4. So lead 2 chloride is going to be a solid insoluble compound plus hydrogen gas. So I'm going to put H2 and a gas. Remember, the 2 comes because it's a Brinkelhoff. Now if I look, I've got one lead, so that's balanced. 1 hydrogen, 2 hydrogens, 1 chlorine, 2 chlorines. So again, I have to put a phase label of 2 out here. And as I go through my reaction types, combination, decomposition, single replacement, double replacement, or combustion, definitely can't be combustion because it doesn't make CO2 and water vapor. Can't be decomposition because it's not starting with one thing and breaking down. Can't be combination because it's not taking two things and forming one. This is another single replacement because you're starting with an element reacting with the compound to make a compound plus an element. Now I would like for you to work through the other 5 problems on this assignment at your own pace, making sure you write balanced equations, trying to add correct phase labels, and then classifying which type of reaction you have. If you have questions, please let me know.